We are the USA SOC Quiet Drone Team, and we were tasked with designing a drone with a significantly reduced acoustic signature than ones typically found on the market. Today we will be discussing the progress our team has made during the first semester of the project. In regards to the project specifications, the final dimensions of the finished drone should be able to fit in the back of a pickup truck with the dimensions of approximately 40 inches by 40 inches. The finished drone must also be able to be flown by a single operator at low altitudes.
After conducting research, we found that a typical quadcopter emits a noise from 70 to 80 decibels. The majority of this noise comes from the propeller spinning at such high speeds that the tip of the propeller creates a very high linear velocity. The frame and the motors also create noise while they are running from vibrations, and the brushless motor creates its own noise. At the bottom are equations to find tip speed and how the sound power will be found using that tip speed. After conducting this research, we found that our final design is going to use shrouds to eliminate the crosswinds from each propeller interacting with each other. The propellers will have larger diameters along with more blades to decrease the rotational speed needed for the thrust. The motors will be brushless, and the frame will be lightweight yet sturdy, so that there will be less vibrations throughout the frame.
The Dayton UMM-6 microphone was used to take audio recordings. The recordings were interpreted using the Room EQ Wizard software to produce a range of frequency and compare it to the decibel level of the recording. The testing apparatus consisted of a 730 kilovolt brushless motor mounted to a 2 kilogram load cell via a 3D printed bracket. An IR optical RPM sensor was used to collect RPM data. The testing apparatus used a microphone, load sensor, and RPM sensor to collect data on different types of propellers.
After the testing apparatus was constructed, 3 different propellers were tested to find the sound created in decibels and the tip speed of the propeller at thrust values between 200 and 600 grams. This first graph shows the data of the tip speed in meters per second related to the thrust. On this slide, it shows a plot of acoustic signature versus thrust. For this test, we collected a 10-second sample of a frequency range of 0 to 20 kilohertz. For the data included in this graph, we decided to use an average decibel rating of 2 kilohertz. The main reason behind this was it was a good average point between the natural frequency of the propeller and also the ending of the recording. As you can see, the 12-inch diameter 3-blade probe has a very similar acoustic signature to the 9-inch diameter 3-blade probe.
Now on to plans for the spring. We will be prototyping different propeller and shroud designs using the testing apparatus. We will also be testing different brushless motors to see which ones are quietest.
Thank you for listening to our presentation.